All right, guys. I was just cleaning things up a little bit, and hey, oh, James, come on over here. Here, could you hold this
Mhm.
and that? And you know what? Actually, that and that. What's the problem?
It's too heavy.
What? What do you mean it's too heavy? What about this is too much?
Everything.
Okay. What are you feeling right now?
Well, my hand kind of
No,
hurts.
no, no. What do you call this thing that you're feeling? This.
Gravity.
Ah. So you're feeling the gravity of this.
Yes. And all the other things.
All right. Thank you, James. All right. So, what did my assistant just say? I loaded him up because, after all, I am a jerk. And then it got more and more and more and more. And eventually he said he was feeling the gravity of those objects. Now, that's what this video is all about. It's about normal forces and the third law. And we're going to go through and think about, are you really feeling the weight of something? Or are you really just sensitive to the normal force? Okay, let's go through that. The first, and maybe the kind of one of the simplest examples, is to imagine that you were pushing against a wall. So, I think who can I pick on this time? Trying to think who haven't I picked on in a while. We could have. I'll pick on Michael because he won't complain. All right. So Michael is going to a restaurant, and he's pushing and pushing and pushing on the door, and it won't open, and it won't open. So I want you to think about, and the reason it won't open, Michael, just in case you were curious, is because it was the outdoor. You're going the wrong way. Anyway, see right here it says pull. Anyway, aside from that, let's imagine instead of a person, or let's imagine, I don't know, that Michael couldn't see, and he had severe nerve damage, and he didn't have any sense of touch. He couldn't sense with his fingertips, and we're assuming he can't see. So, unbeknownst to Michael, George, being the really helpful person that he is, actually opened up the door and replaced it with, I don't know, a giant boulder. Now, think about it from Michael's point of view. Is there any difference? If we don't have a sense of touch and you can't see, well, then it effectively is the same in terms of Michael's motion. In either way, he can't move forward, okay? And that's kind of the idea. The only thing you really know about is the immediate normal force. We don't actually know necessarily, or I shouldn't say that. If we don't have eyes and ears and senses, then we wouldn't really know anything about the details of the boulder or of the door. That's their property. That's their feature. Okay, so that's the basic kind of an idea. Let's do another one. Let's imagine that you have your hand out and, ooh, kind of a stumpy thumb there. There you go. And I were to put on top of your hand a textbook. Okay, and I rest it down there. Now, in everyday language, so our hand doesn't have any eyes. It doesn't have any ability. It doesn't think. Okay, so now it's getting back towards the example with Michael. So the book goes down. Now, in everyday language, we would say, oh, I felt the weight of the book. But is that true? Is it really true that you felt the weight of the book? So here's the thing. How did I draw that? I actually drew it with the book still in the air. So if I hold the book up like this, I don't feel anything, but the book still has weight. So apparently, the thing that I'm sensing isn't actually weight. What I'm sensing is normal force. Okay, so the quantity that we are sensitive to, the pressure that we feel, is all about normal force. Now, if I hold the book still and there's no net force, so there's no acceleration, it's in equilibrium, then the upward force from my hand on the book is exactly equal and opposite to gravity acting down. Okay, and that's, so when we say that we feel the weight of the book, we actually feel the normal force of the book, and we sort of conflate the ideas. Here's another way to say it. The weight of the book never changes. But if I do that, I mean, the force that I'm feeling is variable. I mean, it's basically zero when I lose contact. Okay, so that's the idea behind that. We measure normal forces with pressure and contact. Another way to say it is, it's always rude. So you should know your own weight, but it's always rude to say anything about someone else's weight. So an object in physics is only allowed to know about its own weight. It's not really allowed to know about anyone else's weight. So let's go through an example and kind of see how Newton's second law and third law couple together to allow us to solve problems. And I think this will also clarify the difference between normal force and weight a little bit. So the idea is going to be that we have 3 books. One, just do it like this, 2 and 3. And we'll go ahead and say they all have the same mass. Okay, so we'll just assume they all have the same mass. And we're going to assume that that we're going to hold them, and we'll go ahead and let things have contact. I just didn't want to draw it. So we'll assume there's no gap there. Okay, so now what we know is, it's harder to lift 3 books than it is to lift 1. So the goal is to kind of understand how it is that even though our hand doesn't directly know about the weight of book number 1, it sure does know when the book has been added. So how is it that information gets transferred all the way down the stack to the bottom? Okay. Well, we're going to be very careful. We're going to keep track of what things we learn from Newton's second law and what things we learn from Newton's third law. Okay? All right. Now, I'm going to start this problem by saying that it's at rest. You're just holding it still. So we'll say for us that means the acceleration is 0 for all 3 objects. Okay, so that'll tell us the net force on each of the objects is 0. That's going to help us get started. All right, so here we go. I'm going to run out of room here shortly. So just try to remember, I've labeled them 1, 2, 3 from top to bottom. I'm going to erase this to make room for my diagrams. And the acceleration is 0, and they all have the same mass. Okay, so let's start this the way we're supposed to. We have books 1, 2, and 3. And we're trying to relate information from book 1 all the way down to the bottom. So we're going to need all 3 free body diagrams. Okay, so let's start with book 1. What are the forces acting on book 1? Well, I would say there is a weight due to book 1. Oh, incidentally, what is the book 1 experiences the weight? What is the source of book 1's weight? What is the object you could imagine such that if it were to blink out of existence, the weight force would go away? It's the Earth. So if we really want to be careful, we could write this as Earth on 1, just to really spell it out. So the source is the Earth and the observer is book 1. And over here, I'd have the normal force. Now, the upward force on book 1 is coming from book 2. So this would be the normal force of 2 on 1. And when you do these third law problems, you want to be very careful with how you label things. All right. Now, let's draw the free body diagram for book 2. Well, what are the forces acting on book 2? It also has a weight. I'm going to kind of draw it a little bit to the side to give myself some room. And that would be the weight of the Earth on 2. There is a normal force of book 3 on book 2. And finally, you know, it's kind of like being the middle child. You get pressed from both directions. Book 2 feels a downward force coming from book 1. So there is a downward pointing normal force. That would be the normal force of 1 on 2. All right. Finally, I come to the free body diagram for book 3. I'll just put it over here. And for book 3, there's an upward force from my hand. And there's a downward force coming from the weight of the Earth on book 3. And there's also a downward force coming from the normal force of 2 on 3. All right. Come back to my earlier observation. When I was talking about book 1, I only include the weight of book 1. This free body diagram does not include any other object's weight. Free body diagram for book 2 only includes the weight for book 2, same for book 3. So this is what I mean when I say that book 1 doesn't know about book 2's weight. It's just, it appears in a completely different free body diagram. It's rude to ask about someone else's weight. All right. Well, you know, the first thing we can do, let me go grab a pen here, another marker. The first thing we can do is identify forces which are related via Newton's third law. So let's do that. Now, to use Newton's third law, the forces have to have the same flavor, and they have to only differ by exchanging the labels. So for example, the normal force of 2 on 1 is going to be conjugate to the normal force of 1 on 2. Okay? Those two forces are connected via the third law. Take a second. There's one more pair of forces which are related. Can you find them on the board? Take a second and look. Were you able to find it? Notice I have a normal force of 3 on 2. And down here, I also have a normal force of 2 on 3. These forces are conjugate forces. I don't know. It's tough. Not much room in here. I suppose this is why people don't lecture from their kitchen. Okay, so these are also related via the third law. Okay, so these are pairs of forces that are connected via Newton's third law. They are going to be equal in magnitude and opposite in directions. Notice this is an upward force, this is a downward force, this is an upward force, this is a downward force, so the directions are opposite. They are required to be equal, always. I know I said that the acceleration was 0, but that doesn't matter. There's no disclaimer on Newton's third law. It's always true. For every force, there's an equal and opposite reaction force. No caveats. They are always exactly equal in magnitude, regardless of anything else in the problem. Moving or not, nothing else, nothing can change it. If you punch someone, their face is hitting you with the exact same force that your hand hits them. There's no difference. It doesn't matter. Nothing can change that. All right. Now, the other fact we had was that the acceleration was 0, which means on each object, the total force, the net force, is 0. So what we find, get another marker, sorry. Didn't plan this one very well. These forces, because the net force is 0, then the magnitudes of these two forces also has to be 0, not because of the third law, but because of the second law, because the acceleration is 0. So in this situation, see how this goes. These forces are related using the second law. All right. So in this situation, I have a normal force of 2 on 1. It is equal and opposite to the weight. It is equal and opposite to the normal force of 1 on 2. But only the normal force of 1 on 2 has anything to do with the third law. This vertical pairing only works out because of the second law. All right, so let's go through and see how we can kind of pull this together. And what we want to do is rank. Let's just rank the magnitudes of the forces. All right. And usually when there's one of these ranking problems, I just start at the top or start at the end. So if it's like a bunch of cars pushing on each other, go to the front of the line. Just start there and then work your way back. So in this case, what I would say is that I have the normal force of 2 on 1 magnitude equals the magnitude of the weight of the Earth on 1. That was because of the second law. On the other hand, the third law tells me that this has to be the same as the normal force of 1 on 2 in magnitude. Those are the same. These are the same. These are the same. But if all objects have the same mass, then this is also equal to the weight of the Earth on 2. That's because of masses being the same. And then, well, look, this force equals this force, and these two forces are equal, and these forces are the same. Therefore, all of these are the same. So now I can turn to the normal force of 3 on 2, and what we see is because the acceleration of this is 0, that the normal force of 3 on 2 has to be twice as big as the normal force of 1 on 2. So, how do I want to say this? So then I will say all of these are less than or equal to the normal force of 3 on 2. Again, I'm working with magnitudes. But because of the third law, this must be the same as the normal force of 2 on 3. And the weight, since all of them had the same mass, I can also include here in the top line the weight of the Earth on 3. So all 5 of the top ones are the same. They are all less than, in fact, they're all exactly half as big as these two normal forces. And then because the net force on book 3 is 0, we see that the hand force has to be bigger than either one of these separately, and in fact it has to equal the sum of these. So this has got to be less than the force from the hand. So I know I haven't done much with numbers here, but the idea is what you can see is that if you compare normal forces as you move down a stack, it's kind of like feeling the pressure. If you were to stick your hand in between the books and feel the pressure at different levels, you would see that the lower you are in that stack, the pressure is going to keep increasing and increasing and increasing. And finally, the greatest pressure would be at the bottom. You know this, right? If you're building a human pyramid, if it came to just the pressure you're feeling, well, the person at the bottom is going to have to support the most weight. Okay? Similar idea. If, let's say, there's a fire burning out of a tall building, and the only way for people to escape is for people to make a human chain and kind of dangle out the edge of the window and let people crawl down. If you have your choice, who do you want to be? Well, the bottom, obviously, because you don't want to get burned. But aside from that, think of it from the point of view of the forces you have to support. The person at the top is going to have to support a much larger force. It is equivalent numerically to the weight of all those people. The person at the top doesn't actually feel the weight of everyone. That person only feels a tension pulling down. But the numerical value of that tension will equal the weights of all the people who are dangling. Okay, so that's the idea. I'm just going to go ahead and kind of rank these and work these out numerically now using all this. So if we say that the weight of 1, or Earth acting on 1, is equal to mg, that's the magnitude, then I would say the following forces. So I have the weight of 1 equals the weight of 2 equals the weight of 3 equals the normal force of 2 on 1, which equals the normal force of 1 on 2 equals these all equal mg. They're all the same. And then what we found was that the normal force of 3 on 2, which equals the normal force of 2 on 3, from the analysis that we just did, that must equal twice any of these. So that's twice mg. And then once you know that, and then you know that the force of the hand equals the normal force of 2 on 3 plus the weight of book 3. So then we end up with the force your hand actually feels equals 3 times mg. Okay, so sure enough, the sentiment is correct, even if the words aren't exactly precise. So when my son said he felt all the weight of those books, he really felt the normal force. However, numerically, that normal force equaled the weight of the total stack. And that's always that's how that always works. As long as there's no acceleration, they'll be the same. If there's an acceleration, then you have to go through, and you can't, everywhere you had the third law, you can still use that because that has no caveats. The third law always works. But where I had to use the second law to relate things, you can't do that precisely unless you know the acceleration. Yeah, just one last comment then. Now that we have the third law, and we've seen how they kind of, the objects push and pull on each other, what we see is that in general, you can take any shape. You can think of a car. Okay. Now, Newton surely didn't know about a car, but his laws still apply to a car. So there's nothing in his laws which evidently limit their scope of applicability. They apply to everything. How so? Well, for each individual, so think about a car. Nobody says you have to treat it as one giant car. You could break it up into little chunks. So like you could have like the front bit down here. Just think of it as being broken up into little pieces, like a puzzle. And it's arbitrary. You can do this in any way you want. For each object or each bit separately, you would draw the free body diagram and use F net equals mass times acceleration. And you would do that separately for all of the component pieces. And the way that you would relate the details of, say, this little bit by the taillight to the overall properties of the car is that at the boundaries between these regions, you would have normal forces. And then you can use Newton's third law to basically say that there's a relationship between the normal forces acting down and the normal forces acting up. And so Newton's third law, quite literally, from a math point of view, provides the glue to kind of hold different objects together. It's how we string together the rules to build up larger and larger systems. And it's the third law is set up so that you can subdivide systems forever. You can make them really small, and apply Newton's laws and then glue it up, build it up to the whole object, or you can apply Newton's laws in one shot and to one large system. Just to see how that would work, go back to the book example. Remember, your hand doesn't have eyes. At least I don't think it does. Okay, so we have book 1, 2, and 3. So if your hand doesn't have eyes, you could just as easily, and Newton's laws don't tell you how to do this. In fact, they say you can slice it however you want. So rather than breaking it up, you could think of this as one giant object. That marker's not very good. Think of it as one giant object with total mass equal to 3 times the mass of one of them. Okay, so just think about this as one giant object. And if you draw the free body diagram for this giant object, what would it look like? You would say, oh, I have a weight going down, and that would equal 3m times g. And then there's the force of my hand, going up. And if the object isn't accelerating, then I know these have to add up to 0. Sorry, I should have had -3 mg there. So what we learned is that the force of the hand must equal 3 times little m times g. We get the same answer, regardless of how we slice the problem mentally. And that's always the case with Newton's laws. The mental picture, the way we break things up, is not physical. Nature doesn't care about how we choose to approach a problem. It just cares about what happens. So, okay. So it's a little longer than I was hoping, but that is how we use Newton's third law to break systems apart and then build up larger systems from smaller pieces, and how Newton's laws are stitched together to describe the entire universe. Because if you can go from one object to two objects, it's like playing Legos. If you can click 2 bricks together, you can click 3 bricks, and then 4 bricks, and then 5 bricks, and you just essentially play Legos and build up the whole universe. All right, see you guys next time.